In this lesson, we're looking at tessellations. You'll identify regular tessellations and create a few tessellations with specific attributes. How are tessellations used in art? M.C. Escher was a Dutch graphic artist famous for repeating geometric patterns. He was also well known for his spatial illusions, impossible buildings, and techniques in woodcutting and lithography. In the picture, figures can be reduced to basic regular polygons. Equilateral triangles and regular hexagons are prominent in the repeating patterns. Reflections, translations, and rotations can be used to create patterns using polygons. A pattern that covers a plane by transforming the same figure or set of figures so that there are no overlapping or empty spaces is called a tessellation. In a tessellation, the sum of the measures of the angles of the polygons surrounding a point at a vertex is always 360. You can use what you know about angle measures and regular polygons to help determine which polygons tessellate. A regular tessellation is a tessellation formed by only one type of regular polygon. In the activity, you'll find that if a regular polygon has an interior angle with a measure that is a factor of 360, then the polygon will tessellate in the plane. For our first example, they ask us to determine whether a regular 16-gon tessellates in the plane. So we're going to pull out our formula for the interior angle of a regular polygon. So we're going to have 180 times number of sides is 16 minus 2 divided by number of sides is 16. 180 times 16 minus 2 is 14 divided by 16 is 157.5. Unfortunately, if we divide 360 by 157.5, we do not get an integer. So we can be quite confident, and there's our little mark for, therefore, a 16-gon will not tessellate in a plane. A tessellation pattern can contain any type of polygon. Tessellations containing the same arrangement of shapes and angles at each vertex are called uniform. The tessellation on the left is definitely uniform because it's only made up of one figure. They're all squares. At vertex A, there are 4 congruent angles, and at vertex B, there are the same 4 congruent angles. The diagram on the right is not uniform. At vertex A, there are 3 angles that are all congruent, but at vertex B, there are 5 angles, 4 congruent, and one of these is not like the others. Again, the diagram on the left is uniform. At vertex A, there are 4 angles that consist of 2 congruent pairs, and at vertex B, there are the same 2 congruent pairs. On the right, it is not uniform because I have 2 different sets of angles. At vertex A, there are 8 congruent pairs, but at B, there are 4, and they are all right angles. They are different than A. Tessellations can be formed using more than one type of polygon. A uniform tessellation formed using 2 or more regular polygons is called semiregular. Fun fact, the word tessellation comes from the Latin word tessera, which means a square tablet. These small square pieces of stone or tile were used in mosaics. Next, they ask us to determine whether a semiregular tessellation can be created from irregular nonagons and squares, all having sides 1 unit long. Now, squares we're used to. We know each angle is 90. Nonagons not so much, so let's check. That's going to be 180 times 9 minus 2 divided by 9, which conveniently the 9 and the 180 cancel. So 20 times 7, each interior angle should be 140. So for each nonagon, our interior angle would be 140, and for each square, our interior angle is 90, and we wanted to add up to 360 is our goal if it's a tessellation. So let's start checking. We can let n be 1. And 140 times 1 is 140, plus 90s equals 360. Subtract 140 from both sides. And rats, that's not going to come out even. We could go ahead and divide it out, but S would equal 22/9, not good. Okay, what if we have 3 nonagons? So that'd be, or 2, sorry, 280. Getting ahead of myself. There's my 360. Subtract 280 from both sides. And we get 90S equals 360 minus 280 is 80. Divided by 90. No, that didn't come out even either. If we try 3 nonagons, 140 times 3 is 420. That's not going to work. That's too big. So the question asked us to determine whether a semi-regular tessellation can be created from regular nonagons and squares all having sides 1 unit long. The answer is no, it won't work. Stained glass is a very popular design selection for church and cathedral windows. It is also fashionable to use stained glass for lampshades, decorative clocks, and residential windows. Determine whether the pattern is a tessellation. If so, describe it as uniform, regular, semi-regular, or not uniform. Well, the shapes all fit together without any gaps, so it is a tessellation. Before we can ask if it's regular or semi-regular, we have to clarify if it's uniform or not. I do not have the same angle at every vertex, so it is not uniform. Now, to be semi-regular, it's a tessellation formed by using more than one type of polygon. A uniform tessellation formed by using 2 or more regular polygons is called semi-regular. So since it's not uniform, it cannot be regular or semi-regular. We're done. This is another example that is a tessellation, but because it is not uniform, we have different angle measures at different places. It cannot be regular or semi-regular. A tessellation is a repetitious pattern that covers a plane without overlap or gap. A regular tessellation contains the same combination of shapes and angles at every vertex.